Hello everyone, and welcome back for part 2 of lecture 14, where today in this section, we'll talk about enthalpy as a state function and why that can be really handy. And we'll also talk about how you can obtain enthalpy values with heat capacity. Now, I also just wanted to talk about the different ways that enthalpy and internal energy are affected. And so we've talked about some of them. We've mentioned that changes in temperature, changes in pressure, and a phase change all can affect your enthalpy and internal energy. And those are the items that we're covering in material and energy balances. However, there are additional factors that can affect your enthalpy and internal energy, which are reaction and mixing. And so when you go after this class, you go to thermodynamics 1 and 2, and those are going to help you address the additional variables that can affect your physical state. And that's also the whole reason you're taking Thermo 1 and 2 is to help you better understand the physical world and understand what the physical limitations are, what is actually possible and not possible. And so I just want to put that out there so you're mindful of it. And now I'm going to remind everyone about some of the assumptions we've made for enthalpy and internal energy, because they'll come into play as we discuss a sample problem that will allow us to take advantage of enthalpy being a state function. So as a reminder, for pressure, when you have pressure changes at a constant temperature, your change in enthalpy and change of internal energy are going to be slight or negligible. So when you have a change in pressure at constant temperature, for an ideal gas, enthalpy and internal energy changes are going to be 0. And for a real gas, you can also mostly make the assumption of enthalpy and internal energy being about 0 unless your temperature is very cold, so a lot lower than 0 degrees Celsius, or your pressure is much greater than 1 atm. And so we can assume much greater than 1 atm probably is around, let's say, 10 atm or higher. And again, just a reminder, your enthalpy and internal energy are state properties. And so they only depend on the two endpoint conditions. They do not care how you get from point 1 to point 2. They just care about you're at point 1 and you're at point 2. And that's going to come into play on this next problem, where for this next one, we have cyclohexane vapor at 180 degrees Celsius and 5 atm is cooled and condensed to liquid cyclohexane at 25 degrees Celsius and 5 atm. The delta A, the change in specific enthalpy for the condensation of cyclohexane at 80.7 degrees Celsius and 1 atm is known. All right. And so there's a lot of stuff going on in this problem. We're starting at 180 degrees Celsius and 5 atm, and we're going to have a condensation at 5 atm to make liquid cyclohexane. And that's fine and dandy, but there's a lot of limitations. And one of the biggest limitations is we just don't have information on all these different possible states. It's really tough to measure all these values, and therefore it makes it very challenging when you're not at a specific condition that we have information on. What do you do? And so for here, we're at a pressure higher than usual. You also have a temperature for the condensation of 80.7 degrees Celsius, and so not only are we going from 180 to 25, we also have a condensation in the middle of that whole process. So there's a lot going on here, and that's going to make things very complicated. And so, we have cyclohexane, we have a vapor at 180 degrees Celsius. We want to get to a liquid at 25 degrees Celsius, but there's just a lot of stuff going on along the way. And so that's going to make it really tough for us to get our change in enthalpy going from a vapor at 180 degrees Celsius at 5 atm to a liquid at 25 degrees Celsius at 5 atm, unless we take advantage of this state enthalpy being a state function. And so that's where we're going to start at a vapor. We're going to lower our vapor temperature we need to lower our vapor temperature. We also need to lower our vapor pressure to hit the right conditions where we know the enthalpy for your phase change. And then afterwards, we will adjust your pressure and temperature again to get you to your liquid conditions. And so what we're going to do is we're going to break that whole process apart and just focus on changing one item at a time. So to start, we can take our vapor and depressurize it. We'll go from 5 atm down to 1 atm. And that whole change we're going to say is a change, or that's our first change in enthalpy. So we'll say that's delta H1. The next thing we need to do is we now need to, since we're at the right pressure for our phase change enthalpy, we can now change our temperature to the appropriate temperature for the condensation. And so when we do that, we'll go down to 80.7 degrees Celsius. We have our second change in enthalpy. We can now that we're at the right conditions, we can do our condensation. And that condensation is our delta H3. And so as the problem statement said, we know that value. So that's good. We can take advantage of that. And now that we have our liquids, now that we have a liquid state, we now just need to change our liquid state or adjust it to the appropriate temperature and pressure. So first thing we'll do is we'll change our temperature, go from 80.7 to 25 degrees Celsius. And then afterwards, we can then adjust our pressure and go from 1 atm to 5 atm. And so therefore, our change in enthalpy is going to be equal to the sum of all those other enthalpy changes. So H1, H2, H3, H4, and H5. And now we're going to have to, you'd have to do the calculations for each of these state changes to get the overall change in enthalpy. But we also can take advantage of some of the things that we just discussed when you assume an ideal gas or a real gas. So for example, we said that changes of pressure at the same temperature are probably going to be negligible at low pressures. And so if we make the assumption that 5 atm is still a low pressure, we can actually get rid of H1 and H5. So that helps us out a bit. We also knew H3. We knew the problem statement said, I know the enthalpy for the phase change at 80.7 degrees Celsius, 1 atm. So I know that. That's great. And the only thing I got to worry about now is just the change in enthalpy as I change my temperature. And so that's H2 and H4. So that's the final question of, well, how do I get those values? And that's where calculating enthalpy in terms of heat capacity can come into play, because there's some way you can define enthalpy in terms of heat capacity and obtain a change in enthalpy. And so enthalpy does change as you change in temperature. And so what we can do is we can kind of use this enthalpy temperature relationship to back out a specific enthalpy and then calculate a change in enthalpy. And so with our change in temperature, right, so we can pick two temperature states, and we see that there's changes in enthalpy there. And we can kind of just make an assumption. We can say that it's, let's say, a linear relationship going from the first point to the higher point. And so we'll look at the change in temperature over those 2 points, look at the change in enthalpy, and you can kind of do like a rise over run, a slope type of a deal. And so for us, we can use that heat capacity, Cp, and we can say that that's going to be the limit as our temperature approaches 0 when you have your change in enthalpy over your change in temperature, right? So we're taking the slope of the line and just assuming it's a very small change in temperature. And now we can then set up a differential equation where we say that the change in enthalpy with respect to the change in temperature at a constant pressure is equal to your specific heat capacity. And therefore, if we do an integration with respect to T, we can get that our change in enthalpy equals Cp, the integral of Cp dt from T1 to T2. And that can be really useful, and that would help us out with our problem, because we would know the two temperatures, and we can get the Cp because that's there are Cp values out there for your different chemicals. And after you do the integration, voila, you have your changes in your specific enthalpy. Now, if you're looking for a change in internal energy, you can do the same thing. The only thing you need to do is change your Cp, and instead you'll have a Cv that you'll use for internal energy. And to get your Cp values for that integration, you can go to table B2. It contains all the Cp data for a lot of substances. And just a reminder, it's under your files, resources, table B1, B2, heat capacity constants. And with this table, there's a couple different forms for your Cp. So there's form 1, which is A plus BT plus CT squared plus DT cubed. And then form 2, which is CP equals A plus BT plus CT to the negative second. And I'm just going to show you on this next slide a little sample of that, where in the sample we've got our table. And if you look at the table, let's say we're looking for acetone, you can see that it's going to mention the form. So it tells you which of the two equations you have to use. And then from there, you'll look up all the constants, A, B, C, and D. And for A, we see it says times 10 to the third. And so when we see that, and if we're looking for acetone in the gas state, we see it says 71.96. Now what that means is that it's A times 10 to the third that is 71.96. So what you need to do is you need to divide out, you need to do 71.96 divided by 10 to the third to truly get A. And you can also double check that with the example problem up above, where it says example acetone in a gas. You see that CP value, the A value we saw, 71.96, they divided by 1,000, 10 to the third. And that's why in the example it says 0.07196. So just be careful when you read the tables, but those tables are going to be really handy to obtain your CP values and then figure out some changes in specific enthalpy when you have temperature changes. And that's going to wrap up this part of Lecture 14 and also Lecture 14, where we talked about how you can take advantage of a state function, and we also define enthalpy in terms of specific heat, which can be useful. So thanks for tuning in, and I hope you have a great day.